So our next speaker is Dr. Said-Recent. Dr. Said-Recent is the, hey, Dr. Said-Recent, are you here?
Can you hear me okay?
Yeah. I
Perfect.
see you, great.
Yep,
Great.
perfect.
Let's make sure you are here. Let me introduce Dr. Said-Recent. He is the CEO of All Cell Technologies, LLC, and also professor at University of Illinois at Chicago. Dr. Said-Recent is the CEO and co-founder of All Cell Technologies, LLC, and a research professor of chemical engineering at the University of Illinois at Chicago. He earned his bachelor's degree and master's degree of science in chemical engineering from Jordan University of Science and Technology, and a PhD in chemical engineering from the Illinois Institute of Technology. Dr. Said-Recent co-authored a book entitled Hybrid Hydrogen Systems and has published several book chapters and numerous peer-reviewed papers. Said is the co-inventor of several issued and pending patent applications in areas of renewable energy, energy storage, and water desalination. Dr. Said-Recent today's talk is on recent developments in lithium-ion battery pack thermal safety. So let's welcome Dr. Said-Recent.
Thank you very much. I'm going to share my screen. Please let me, if you can see it okay. Good. Okay. Can you see my screen okay?
Yes.
Okay, perfect. Well, thank you very much for the kind introduction, for the opportunity. Here's a quick overview of the presentation. I will try to do a little bit of both. First, just give you an idea where we think the energy storage, especially lithium batteries, going in the case of the mobility application, electric mobility. And then I'm going to focus on the issue of safety, thermal management, and present to you as a passive thermal management solution that we developed at All Cell, and share with you some of the work we're doing with national labs. Probably, the core of the conference talks about global climate effect and decarbonization. And one of the challenges that we found for a while now is how can we transition from an oil-based or liquid fuel-based transportation sector, which is monopolized by liquid fuels, to an electrified system that can be powered by energy from renewable and non-renewable sources. And then the way we've seen in the last 2 decades, probably most people noticed that the introduction of the hybrid system was the first step, and gradually we're moving toward electrification, full electrification, which can be powered by batteries, ultracaps, and fuel cells. So it opened the door for various technologies. The technologies that we see that going to be probably the biggest challenge today for such transportation electrification are the energy storage, onboard energy storage. And batteries like lithium-ion have been around for a while. Cost is still an issue, cycle life. And safety, as I will probably touch on in the next few slides, will probably be a big one. Lithium-ion batteries have shown big strides. We'll share with you some of those development, but we hear a lot of talk about fuel cell and hydrogen. I think the next section will talk about the hydrogen economy. And in that, you will see that the challenges there are a little bit different. We still have some major infrastructure challenges, but onboard hydrogen storage is still something that fundamentally needs significant investigation and significant investment in discovering new material that we can store on board for hydrogen-powered cars. I want to share with you some of what you see here happening in the industry and the government. I don't want to go in details, but you can see that it's apparent now. A few years ago, people were questioning what's going to happen. There was some resistance, but you see countries are moving rapidly toward actually banning non-electrified or diesel or pollutant type of vehicles, especially public buses in China and Europe and in the US and California. And companies have joined the race full force. And you see it varies from companies announcing various models in electrified, fully electrified, to companies who decided that very soon they're going to completely go out of the combustion engine business. And we're going to continue to see that trend, and we're going to see continuous investment and both the internal development, but a lot of acquisition we're going to see by the industry in the next 5 to 10 years to see who is going to be able to position themselves for the future. Here's just a kind of an electrification continuum, which is basically shows you what's happening in the transportation industry. In the case of passenger cars, we've seen this happen over the last 2 decades. You can do hybridization for multiple reasons. You can do it for efficiency to meet regulatory requirement. For example, a start-stop battery now is very common, and that can save you a few percent to boost your miles per gallon. But this one is not electrified, which means the drivetrain is still mechanical, and the battery only serves to power the auxiliary needs while the battery is stopping in a light or in rest. All the way to the right, you see the full electrified system that can be powered by battery fuel cells. And those can be fully electric or can be plug-in electric. The full electric, you have anywhere between 100 to 300 miles drive range, while the plug-in, you have a drive range about 30, 40 in full electric. And then you have a small engine actually in the back that works as a power generator to power the vehicle till you gas up or till you fully electrify. In the middle, you see the mild hybrid and full hybrid, which is all of those are fully electrified drivetrain systems and then can use hybridization by a combustion engine. These are examples that you see that you're going to continue, but the challenge going to be here for most industry is how to create platform of energy storage that both scalable and cost effective. What is fascinating about this is basically the technology is there. We've seen companies get you 200, 300 miles. The challenge is cost. Today, the automotive industry transition to electrified has been an eye-opener. The battery cost, and for fully electric vehicles, for example, like the Tesla and the others we drive over 20 miles, is more than 50% of the total cost. This is something new for the automotive industry because basically you have the whole thing just carrying a battery, and that's pushing both the technology innovation, but also from a cost viewpoint, unless those batteries cost significantly reduced, you're going to see a big challenge of how to go market scale. By the way, today, the total global market share for EVs or electric vehicles is about probably less than 2% sure, but around 1%. So there's a long way to go before we see massive market share change for EVs. There's other mobility applications that we at Wholesale has been focusing on for the last 5 years. And those are, as you can see to the left, these are always anywhere from commercial drones that you see delivering package to can also delivering medical supplies in rural areas to electric boats, autonomous vehicles. But we've seen a push toward various type of airspace kind of application. We're not talking yet about full electric planes, although that's happening. But we're talking about, for example, the electric taxi, as probably you will see people talking about it, which is an electric vehicle takeoff and landing vehicle that can replace the helicopter and reduce their cost. What you see in most of those applications, it's pushing the envelope on what these batteries need. So you need very high energy because driving, but you need very high specific power in order to do the lift and the acceleration. But in all these, safety is still a big factor, and in some cases actually is becoming a hurdle for deployment of those new technologies. Here's some sort of a roadmap. This is simplified, but just to give you an idea, people ask what's going on. Lithium, solid state, beyond lithium. We've seen the lithium-ion battery do a very good job over the last 20 years of consistently increasing energy density and power performance and reducing cost by 5 to 10% year after year. That was done through systematic and incremental improvement with the small format cylindrical cells that 18650 and 21700 that Tesla and you see in personal electronics. Those will continue to do this for the next 5-10 years. And what we've seen, for example, one transition in the past couple of years is that we moved from the small 18650, which has 18 millimeter diameter, to 21700. And that was not changing the chemistry, but changing the active material to the case ratio, which increased the energy density. And we'll continue to see some sort of improvement over the next few years. At that point, you're going to see more and more trend to solid state batteries. And those have been interesting because the key part of the transition to solid state is to get away from the electrolyte that is currently in the lithium-ion battery, that most researchers agree that is actually the source of safety problems and some of even the performance and degradation. So the promise of moving to all solid state is something that everybody's looking at, and there's a lot of research on it. There's some small scale, but I don't think we're going to see in high volume and high, passenger application anywhere in the next few years. I'll touch on that. Beyond that, there's a lot of interest in what's called lithium iron and lithium sulfur batteries. We've seen some of that actually, some companies now is manufacturing, but again, I have not seen anything in high volume yet, which talking about today, the small cylindricals, they're making billions every month. I don't think we're there yet with solid state and lithium or lithium sulfur. Here's an interesting trend. This graph published by Bloomberg, we were part of the contributors to the study. And as you see, what happened over the last 10 years, probably a little bit, the solar energy industry, made a huge impact by reducing cost, below $1,000 per megawatt. I've been working solar energy for over 2 decades, and we were always dreaming of getting below $1 watt or $1,000 per kilowatt, and we've seen that. And now, as that happened, quickly we're finding out that the problem is how you store that energy, which is the topic of this presentation. And you'll see, like Ludiger mentioned, you're going to have to look at seasonal storage. You can have thermal. You're going to look at all kinds of storage techniques, but that is going to be probably very challenging, and the biggest one to get renewable energy to higher penetration, reduce cost. In the same time, we've seen lithium-ion batteries going into electric vehicles, and the cost has been dropping significantly. If you believe what you read in the newspapers, you see today, lithium-ion per kilowatt hour is actually at or cheaper than lead acid. And that's a big deal. If you're talking about lead acid batteries in general, they have been around for decades. And the fact that the cost is getting there, that is the point where we're going to see literally an inflection market exponential growth, because lead acid industry is already tens of billions of dollars. If lithium can replace it and continue to grow in new market like renewable and EV, it's going to be fascinating to see what the storage industry is going to do. So if you're in the energy storage business, I think you're going to be busy for decades to come. I'm going to shift to talk a little bit about thermal management of lithium-ion battery. Why? The reason that is important, and I think Professor Unry is going to discuss that in more details in the next lecture. So I'm not going to go in a lot, but I'm going to just touch point about why it's important. Safety and thermal management is important. Lithium. So as you can see in this graph, lithium-ion batteries are actually the optimum point. Is very close to the body temperature, to human body temperature. That is actually when the desired operating temperature and when the electrochemistry and the performance and the power is at its best. As you go above that, you start seeing some non-chemical reaction, and I will show a little bit of that in the next couple of slides. That will lead to gradation, and if you keep increasing the temperature without control, you risk thermal runaway. However, if you go to the left, which means the temperature starts going below 0 Celsius, because of the liquid electrolyte, has a lot of those chemicals that will start freezing, you will start seeing sluggish electrochemistry. And as you can see, as you go below 0 Celsius, you're going to have problems with both getting capacity, but the power is going to be also very problematic. And that's the challenge for lithium-ion battery, thermal management, is how can you keep it at that optimum temperature to both improve performance, but also to keep it safe. The reason that's critical, because we found, and we published this work, we did work on energy storage for smart grid application. We were one of the first group to deploy that in the PJM area for frequency regulation and peak shaving. And when we studied that, we were trying to optimize the battery. We found actually, like you see in this graph to the left, when lithium-ion battery temperature goes from 25 to 45, the cycle life drops significantly. And the reason, as the graph shows to the right, is the impedance growth. And that is an area by itself, impedance growth. And the next slide, I'll just touch base on it. But again, I think Professor Nori will explain it more. Also, we noticed, and this is also documented, we'll publish, that if you decrease the window of operation for the battery by just 10%, going from 4.2 volt at the top to 4.1, again, you see significant improvement of the cycle life or reducing that impedance. And those are the things that are, any battery management system has to do, and the engineers and designer have to take care of that. What is the batteries doing, electric car or storage, stationary storage. Here's the study we did with the National Renewable Energy Lab, and what we did a thorough study of the cell that we tested in smart grid application. I'm not gonna go again in a lot of detail, but you can see the calendar life and the cycling, both are very sensitive to both temperature, but also window charge discharge. So for example, if you narrow the voltage from 95% to 80%, we've seen the battery cycle life goes from a few hundred to a couple of thousand. And you can go to tens of thousands if you narrow to 10%. And some people ask why 10%? Well, most of the money actually in a lot of areas in the frequency regulation is not in energy, it's just in power by balancing the grid because of the high penetration of renewables creating imbalance to the grid. So the storage here, I just want to, it's fascinating in this session that you can see the storage dollar value, as the previous speaker, Ludger, mentioned, in seasonal, it's totally different than in grid stabilization. Here we're talking about seconds. The value per dollar value per second is much higher than minutes or hours or days, but again, it depends on the application. As you can see from this slide that we did a little bit of more investigation, we found the reason those batteries suffer is because you have what's called the growth of the SAI layer. And then also because of fracture, we developed empirical model, physics-based models that actually help us both try to predict and optimize the battery, but also they serve in the BMS to fine-tune the battery as we use it over time. So what you see today in the automotive industry, or most, they look at two types of thermal management with passive, which is liquid or air. And those are well commercialized, well defined, but as you can see from this slide, the two issues that we found is that none of them can stop thermal runaway propagation, which we will discuss in a minute. In addition, if, like you mentioned, Ludger mentioned, if you're in North Europe or North America, the temperature in winter is very low, below 0 Celsius, maybe 10, 20, 30. And at that point, most drivers notice that the battery itself, drive range will drop by half or maybe more. But on average, we found that the battery loses almost 20% of its energy to do a desired thermal management. And that is something that is very expensive. So you're talking here not about the cost of the system itself, talking about the energy that's stored in the battery that costs thousands of dollars that is needed to maintain the battery thermal management. Here's some examples that you see, and it's unbelievable, the engineering marvels that the industry has developed. For example, the one in the middle of Tesla, they developed microchannels that goes around thousands of cells to keep the temperature uniform below 5 degrees C. You also see in the Volt that developed those 2mm microchannels, cold plates that goes between pouch cells that they're amazing from a design viewpoint. Unfortunately, when you have hundreds of seals and you have any of those seals leak, any battery engineer will tell you that's a nightmare. So those, it's there, it's been working very well, but we think there's room for improvement. This is what we developed, and thanks to Ludger, I don't have to explain phase change, latent heat. Again, we use paraffin wax, which the one we use about 45 to 55 C range, depending on the chemistry, can give you, the wax itself can give about 200 joule per gram. However, because of the issues that subcooling and the issue of thermal properties or thermal conductivity that the wax has, we actually impregnate it in graphite. So the graphite matrix helps to microimpregnate the wax. So actually the wax does not leak, that does not deform. What you see here, the black matrices here are like crayons that they soften during the transition, but they don't leak and don't deform. The other property for the graphite, as you can see in this slide in the middle, when you do not have PCC, the temperature continue to increase. But when you have PC in the bottom, the wax start melting, control the temperature, and the graphite spreads the heat because it's a very good conductor, and you end up with the uniform temperature across the pack. This is critical, as I mentioned, because it improves performance and it reduces degradation. Here's a case study we've done with a commercial drone. This company, we helped them by, their pack without thermal management would probably shut down about 60% of the time after takeoff. Would not utilize the full capacity because the temperature exceeding the safety limit set by the manufacturer. We were able to add just about 8% of phase change limit around 48 degrees Celsius, and we bought them 40% runtime, which, by the way, in air transportation, this is huge. But this is just an example of how we were able to, just by bending the curve in red, buy them extra time to utilize that energy. I want to talk a little bit about safety. As you can see from this graph, these are incidents that are taking place today of high profile, and nobody wants to make the front page on those. Those are well publicized thermal safety fires that happen in the industry. And what the reason is, what most people discovered is that actually that's one of the cells has, this is beyond 6 sigma quality, but one of those cells in a few million is going to fail catastrophically. And if you're not able to stop it or contain it, then it's going to propagate and cascade into thermal runaway propagation. And that's what's called, that's what causes the domino effect that causes that. We developed ways to test those batteries. This is well established in the polymer industry. It's called the accelerated calorimetry. What it does, you put the cells inside. It's like a volt. You put the cell in, you start heating a cell, and then you wait in the wait period, and you keep the temperature constant and start looking for exotherms. Once that exotherm triggered, the arc start accelerating, keep it adiabatic, and then that way you can actually quantify the trigger temperature, so you can keep the battery below it, but also you can measure the thermodynamic kinetic, and you can use that in modeling to develop safe systems. We've tested almost most of the commercial cells in the market today. The 18650, anywhere between 3 to 3.5 amp hour, and the 5 amp hour, which are the new cells. And what you see here, once you go above 100 C, the batteries start going to thermal runaway immediately, and the temperature increases per minute is very high. Basically, most of those cells will go from 100, 110 to increase by a few hundred degrees in less than a minute. And that's critical to understand, because that means it's a combustion reaction. And to design a thermal management to do that is going to be very challenging. And there's very little you can do once that happens, except containing that cell and preventing the heat from going to adjacent one. We've done a study with NASA a few years ago on actually looking at various materials inside the pack. The pack you see here in the picture is an electric bike pack, has 40 cells connected in 10 in series, 4 in parallel. That's about 36 volt, few hundred amp hour pack. And we used filling material, first air, graphite wax, and graphite wax. And the idea here, as you can see, we did nail penetration tests. So we force one cell to go into thermal runaway and see what happens. We've done this work a few years ago with the National Renewable Energy Lab. And as you can see in this graph, the one to the left, which has air only, the first cell fails, and a few minutes after that, the other cells start popping, and you end up with a fire. The one to the right, once you do the thermal runaway, force the thermal run in the first cells, the other cells start heating, but if you keep it below the 120, 130, then they go cool down, and you save the day. This is a summary of all the different material we tested. As I mentioned, air is a good insulator, but it cannot spread the heat, and then the cells either heat up. Graphite alone is good, but it cannot control temperature because it's only sensible heat. Wax is good, but the problem with wax, it's an insulator, so it actually exacerbated the problem. But the last one, which is phase change composite, you get the best of two worlds. You get wax with latent heat that can absorb it, and graphite that can spread it and make sure that you don't have concentrated hot points. This is an autopsy we did after the one to the left. You can see the cell that failed was contained. Nothing much happened to the rest of the pack. The one to the right, we actually had to pour water after the first 2-3 strings of cells failed. And you can see that they're charged, and it was not pleasant. It was, by the way, Sam Plunkett, who's my associate and colleague who did a lot of this work, is in the call. I think he will be happy to answer some question how fun it was just to blow up these batteries. One couple of things we noticed that I want to share with you. The one to the right, that we found that there was some side ruptures. These batteries have vents that's supposed to push the electrolyte out to keep it from exploding, but we found that a lot of cases they side rupture that actually a problem, because you end up with a torch that is going to be directly exposing the other cells to failure. The one to the left, which is interesting, we found actually the thermal failure that happened to the cell was not the only culprit that causes the thermal runaway. There was the nickel clad, or the current collector we found out, caused actually significant short circuit, and the other cells start dumping currents. And this is something that pushed us to study this. So what we did actually, and this is common, and we found that actually some of the regulation that when you do test a cell, you make that cell fail, but electrically is not connected to their spec, which actually in the left one to the left, you can see it passes. The temperature stays below 100, you're okay. But if you connect it electrically, the one to the right showed you that something happened there, that these cells continue to heat, and you end up in thermal runaway, which is the same pack, which is fascinating. So Sam and our team did more studies on this, and we actually took the cells themselves and we forced circuit discharge, or short circuit, and we found that there's a device called the CID that is supposed, when the cell fails, supposed to disconnect it electrically and prevent it from dumping current. Well, what happened is we found that those devices, it takes it 2 to 3 minutes to fail. And as you can see from the current here, the spike of current is about 50 amp, and it runs for 2 minutes. or 3 minutes at above 30 amp, which basically the battery is heating itself significantly. So you have the pack where all these cells are dumping current and overheating themselves, and that leads to thermal runaway. We developed what's called engineer fuse. You see most battery manufacturers have their own proprietary design. And when you fuse it, basically, if one cell fails, you actually disconnect it. And as you can see in this graph to the bottom right, that when you do that, you prevent the current dumping. And that way you don't end up with the thermal runaway, not because of thermal, but because of the current dumping mechanisms. We found another problem that actually the industry is trying to figure out with new regulation. So you're going to see a lot of push for new regulation from UL called the 9540A. That basically what it requires from you is to do two things. First, you have to stop propagation, which I demonstrated that we could do in the previous slide. However, there should be no flame. And you can see the graph in the left. When one cell fails, that electrolyte is very flammable hydrocarbon that start venting and cause you flame. Now, the problem is the real regulations say you cannot have flame escape. So what you have to do with the failing cell, you have to find a way to prevent that flame from going out. And what we developed is a new technology that actually we just filed for IP on that patent, which is basically a combination of monofaulting in the top of the case of the pack that is end up with a trap, which is a thermal fuse with hydrogel. Hydrogel is a polymer, super absorbent polymer that can absorb water 10, maybe 100,000 times. So if you microencapsulate in a pouch, as the flame is directed through the manifolding, then it can go through that pouch of hydrogel. And as our previous speaker said, when you go from liquid to vapor in water, you have a heat latency that is an order of magnitude higher than ice. And that way you can have massive latency that can quench the flame, but also important, by releasing the vapor, you reduce the vapor contact or vapor concentration. So hopefully, if you do it properly with the proper venting, then you can dilute the flame and you don't allow it to catch fire, and then you can vent it safely to the environment. Finally, I want to just tell you a little bit about work we've doing with the National Renewable Lab and Shell. Shell has it's like a challenge called the Game Changer. This year was about fast charging. And what we did, we developed a technology, I'll show you a little bit about it. And then we're working with National Renewable Lab, who've been working with us for the last 12 months to basically develop the algorithm and actually validated our theory, and hopefully we'll build a prototype and demonstrate it soon with our partners, National Renewable Lab and Shell. This is just a quick idea of what it is. Basically, a lot of people are thinking about fast charge. When you have an electric car, you don't want to wait for hours or even half hour. You want to fast charge it. And when you do that, fast charge for lithium-ion battery, especially high energy one, the manufacturer won't let you fast charge it more than an hour, or in 30 minutes, 80%, most of them. And that's the challenge. What we discovered is if there's a combination of what's called, if you have an intelligent battery thermal management that combine electrochemistry, optimization of the cell by heating it or cooling it, with battery management system that can control and balance the batteries, and power electronics that can dynamically create an optimal charge discharge, you can actually end up with the best of two worlds. You can have a high energy battery that's used in for example, the energy application, but you can fast charge it by that control. And then if you do that, as you can see to the left, fast charging can be a huge part in fast charging of electric vehicles, mobility, even robots, but also it can buffer the grid. From when you have fast charging of cars, hundreds or thousands of those cars, the grid cannot take it. So you can use it both to power the grid, but also you can use it to store renewable energy. And we think that's going to be battery buffering with fast charging is going to be something that's going to be deployed massively in the next 2-3 decades. Here's an interesting, this graph. This is in the literature, you'll see when you go charge the batteries, high energy batteries above 1C, it's not recommended. So what we did here, we found, and actually this is published in the literature, those high energy batteries, which is from NCM, nickel, cobalt, manganese, and even graphite, when you fast charge at 2C rate, if the temperature is about 35, the battery starts failing catastrophically after 50 cycles. If you heat it up to 45C, you can have 2C charge maybe higher with no problems. Now, the reason is because, as mentioned earlier, around 45C, you have the optimum electrochemistry and ion diffusion, and you lower the resistance or the impedance for lithium movement and allow you fast charge. But at the same time, and the graph to the left bottom, you can see if you have PCC that controls the temperature increase beyond that limit, then you can do that safely without degradation by controlling the temperature and keep it constant with the red line seen there. So the idea working with NREL, we can develop models, physics-based models that we can actually optimize the battery operation at the right temperature by providing the controller and heating and cooling as needed. Then you can have, optimum phase change composite with battery management that allow you to fast charge the battery. Our goal right now is to be able to fast charge these batteries more than 50% in less than around 10 to 15 minutes. And we think, this may not be a big deal, but for a lot of our applications, the economic benefit for that are tremendous. So in conclusion, I just hope that this just gave you a way of just an idea that lithium batteries are powering electric mobility. They're going to continue to do that in autonomous vehicles and planes for a while. The cost of lithium battery and continuous improvement are playing a big factor to continue to do that. We truly believe that thermal management, safety of lithium-ion battery are areas that have to be taken a look at, and you're going to see more and more focus on it as the energy increases and the safety become an issue. And finally, we see there's a trend of new battery technologies coming on the way, but I still believe that's going to be probably 5, maybe 10 years away from commercialization. Thank you for the opportunity again, and I would like again to acknowledge my colleagues, especially Sam, who's on the call. Thank you very much.
Great, thank you, Said, for the great talk and for introducing this amazing technology to us that can potentially save people's lives.
Thank you.
Yeah. So there are questions from audience. Specifically, Ludger asked a question. How about direct cooling with dielectric liquid oils?
You know what, Ludger, I would love to chat with you on that. I'm not an expert in that topic, but as I mentioned earlier, you'll see that phase change material, I worked on it 20 years ago in Jordan for storing heat for solar heat. When I came to the US, I found that actually phase change material can play a big role in thermal management, in batteries, ultra caps, laser guns. A lot of those, the current technology, we actually, even with microchannels, you see that cannot do the job of containing heat. So I think phase change is going to be there's a lot of room for phase change to play in thermal management of power electronics, chargers, and batteries. Because what's happening is the electrical engineers are beating the crap out of us with physics by going exponentially faster, but the heat generation is still constrained, and that way thermal management is going to still have to keep up, and we have not been doing a lot. So phase change, I think, has a big room to play in this area. And I would love, Ludger, if you have ideas, I would love to work with you on it.
Yeah, next week we'll have a talk, a private Zoom talk about that.
Fantastic.
I have a couple of ideas on that. Yes,
that would be great.
Yes,
Thank you.
Perfect. Yes, excellent presentation. Thank you. I love that. Yes. Yeah.
Thank you.
Ludger's question, right? So, can you share with us Can you share with us your story about how did you narrow down to this specific combination of wax plus graphite?
Yes, sure. So I mean, 25 years ago, I came from Jordan to do my PhD at IIT, Illinois Institute of Technology. And at the time, IIT was awarded one of the first largest lithium-ion, actually power packs for Soldier of the Future program by the Army Research Office. And as a chemical engineer, I was thrown into, I've never known batteries, but I wanted scholarship. So my professor said, do you know batteries? I said, are you kidding? My middle name is batteries. I knew nothing about it. But when I started looking at lithium battery, what was fascinating, when I started doing research studies, we found that lithium batteries actually have a huge entropic effect, which means that during charge, it cools down because of the cathode lattice, and during discharge, heats up. So from phase change material, we know that is actually perfect because during discharge, it can absorb the heat, and during discharge, I can let it go. So that's how the idea sparked. That was my PhD work. Soon after that, when we started doing work, we noticed that the problem phase change material, probably Ludger would tell you, they have terrible thermal conductivity. So we tried to find ways to contain the wax. And like I want to say we're geniuses. We tried everything. Like Edison, we tried ceramic, metal, foams. We tried everything. And we work with people in Guangdong, for example, researchers on copper. But graphite happened to be one of the best ones. It's used in anodes. I have a strong familiarity with it. And what was fascinating, when you press the graphite, expanded graphite, you end up with micro tortuosities that can encapsulate microgravity wax, and it doesn't escape. And actually, it's flame retardant. So I would say it's both being at the right place, luck, and hard work to solve some of the problems.
Great, yeah. So, you mentioned that Tesla has this current cooling system that is very well engineered. What is your vision about your technology, right? So is that to combine with the existing system, or you think it can competitively replace these existing systems?
Yeah, so what we have done with the other application that can tolerate, so that when you are a startup, this is something for people, when you're a startup, there's two problems that we face, and it's called the death valley. One of them, when you work big companies like Tesla and in your startup, it's very dangerous because the supply chain has to be stable. So it's very hard to get a big OEM to work with a startup. And we actually guilty. We did not understand that till recently. The other challenge that you have is scaling. A lot of time when you have a great technology, and startups are very good in inventing new solution, but we're terrible at scaling up. You need new talent. It's not just money. It's the mindset. So to be a tier one supplier to the automotive industry, it's totally different from, for example, our customers today and robots, planes, it's top 10 companies in the world, names that everybody knows that do electric planes. They come to us, we're comfortable working with them to build tens or hundreds. When it comes to automotive, as a startup, we found that we do not know what the requirements are. So now we're switching actually. We're now literally, the first thing to do is to fire the innovators and bring people who can actually scale and understand what it takes to scale. And that has been our challenge. It's not that the technology doesn't work. It's just that we as entrepreneurs did not understand what it takes to take a technology and make it a scalable tier one supply. And that's what the transition we're going through.
Great. Yeah, so let me ask you the last question from the audience, also from Ludger, saying that, can you explain more in detail the mass content of PCC on slide 16? Is it 4 mass percentage or something like that? Yeah.
Yeah, so slide 16.
Yeah.
This slide, right, Ludger? Yeah. So basically, weight and volume are very expensive commodities when it comes to electric planes and drones. And what we discovered, as you can see in this example, we did extensive modeling work, and Sam would tell you, when we do this, we do a combination of thermal runaway tests, we do very good heat transfer, and we do complex finite element modeling. And the goal here is not to do, anything more than give them enough material to allow them to go to 100%. So based on testing and basic experiments, we found that it's only 4 grams, which is about 8% of the total mass of the battery. In this case, we found that the most case we were adding only 12% to the total mass of the pack, which is significant. At that, you're probably better than liquid, but you're worse than air. But with the value we bring, we're now getting to the point where we're becoming a good solution.
Great, thank you. Thank you, Dr. Said Haji, for the great talk. And Said will be here with us in the coffee break. If you have more questions, sure. He's glad to discuss with you.